Hello and welcome to the 12th and final part of this Introduction to Haskell course. And in this part, we'll be talking about monads. Now, monads might be quite difficult to grasp at first, and I guess that's because they have a root in mathematics, in category theory. So we can think of monads as a mathematical entity, but we can also think of them as a practical entity. And the mathematical entity is far more harder to understand. So we will deal only with the practical entity, or in other words, we will explore what monads can do for us in Haskell. Monads are a type class, much like the functor and applicative that we covered in the last two videos. And monads generalize the idea of programming with effects and also chaining operations together. So programming with effects, meaning basically programming with effectful arguments. So maybe type has its own effect, the possibility of failure. The IO type has the effect of interacting with other systems. And we'll see how monads generalize this way of programming. So they're used to structure programs more generically and avoid code duplication. And to illustrate this, let's go through an example. If we have a database with accounts and transactions, so a simple database, just accounts and transactions, we represent the transactions and accounts both as just a string. So this is just a type synonym for transactions and account. And now imagine that we need to create a function that is a lookup of accounts given a transaction from and to. So we need to find the origin account and the destination account given a transaction. In that case, we have three main ways that our function can fail. The given transaction is not found in the database, the origin account is not found in the database, or the destination account is not found in the database. So if we were to write this function with what we already learned, this is not a full implementation because I just put the three functions here, find transaction, find origin transaction, and find destination account as a sort of a placeholder for these functions. But we can just imagine that we have a function that given a transaction gives us back a transaction, a maybe transaction, because that transaction either exists in our database or doesn't. So the find origin account, the same thing. If we give it a transaction, maybe we get an account back, maybe not, all right, because it can either exist or not. The same for find destination account. So we don't have the actual implementation for these functions, but we can imagine that they exist. And now if we want to define a function that finds both accounts, the origin account and the destination account given a transaction, then our type signature is from transaction to maybe tuple of two accounts, the origin and the destination. And so to program this with what we already know, we can say find accounts for a transaction is equal to, first we have a case of find transaction t, so apply the first transaction to check whether the given transaction really exists in our database. And if we have a nothing, then we say this whole thing is nothing. But if we do find a transaction, then we go to our second step in our pipeline, which is to find the accounts, or we start with the find origin account. So we know that this transaction t does exist. So we call find origin account of t, and then again we can have the origin account in the database, or we don't have to. Maybe something went wrong and there is no origin account in the database. In that case, we would get nothing. And we again say then the result of this whole thing is nothing. Or we do find the origin account, And we say then in that case we proceed to the next step, which is to find the destination account of the same transaction T. And in that it can also fail. We can either find it or not. So we can either have nothing, in which case we again return nothing for everything, or we have just destination account, and in this case it's the final step for our pipeline. So we have everything, we have found everything that we needed, and finally we return the just constructor for the maybe type and our tuple of origin account and destination account. In that code segment, there is definitely a pattern of checking for exceptions at every step, right? All the time we are checking what is the result of this step. Is it a nothing or is it a just? And then we have to explicitly define those checks every time. And so we end up with complicated and hard to read code. We end up with 3 nested case of statements. It doesn't look very good. It's kind of very long for the simple thing it does. So since every step of the function depends on the result of the previous one, we can say that it binds to the result of the previous one. This is exactly what we can abstract out with the monad class. So here's the class definition of a monad, and there is a class constraint of applicative M. So any monad M must first be an applicative, and the methods of the monad type class, the 2 most important ones are return and this bind operator, the greater than equal to operator, which we refer to as the bind operator. There are some other methods in the monad type class, but definitely the most important one is the bind operator. And if you can understand that one, you won't have a problem understanding the other ones. So starting with return, it's a pretty simple method that simply takes a value and returns a monadic version of that value, wraps the value into the monad type. In most cases, return is going to be the same as pure from the applicative type class, right? Which also takes a value and wraps it into the applicative type constructor, or returns the value in that type. So that's pretty simple. The bind operator is more complex. So the type signature of the bind operator is MA, so a monadic value of A, then a function which operates on the type A that the monadic value is holding, and the function returns another monadic value of B. And finally, the result of the whole thing is monadic value of B. So basically what happens is you take a monadic value of A, you give it a function that operates on A, bind operator extracts the A value, applies the function to it, and returns a monadic value. It's important that both the start and the end are both in monadic values. With monads, most of the time, I think once you have monads are kind of like encapsulation as well. So once you get a value into a monad, you can only really work with it inside the monad. This is not always true for all types, but it is an important concept, especially for the IO type, right? The IO type, we said, represents the impure world, and once a value is turned into an IO type, once there is some side effects going, there is no way anymore to get that value without it being wrapped in the IO constructor. So it's always encapsulated inside the monad. And that's sort of what protects our pure world and our impure world from ever mixing together. Now let's take a look at the maybe monad, or in other words, how the instance for the monad type class is defined for the maybe type, which it is defined by default. So we need to most importantly define the bind function, the bind operator for the type when we define a monad type class, an instance for the monad type class. And so the type signature, based on what we saw on the previous slide, for the maybe type, it's going to be maybe A, then a function that operates on A and returns a maybe B, and finally the result is going to be a maybe B, which is the result of applying this A unwrapped value A to this function, and then we get a maybe B. So first of all, the nothing case is pretty simple. If we get, if our maybe A type is nothing, then we can say we don't really care about this function because we are going to propagate the error or the nothing. But if our maybe A value is some just X and we are given a function, then then this bind operator, what it will do is simply apply f to x unwrapped here, right? So we have just x here, function operates on x, and the result of this function is maybe b. So we don't need to wrap anything into a just constructor. The function already returns a maybe type. Now we can rewrite our find accounts function using the bind operator from the monad type class, since we know that maybe is an instance of the monad class. Our type signature stays the same. We want to give it a transaction and we want to get back a maybe tuple of accounts. So find accounts T means find transaction T first. The result of this find transaction T is, as we know, maybe transaction. So it's our MA type for the bind operator, the first argument. And then we bind that to the second argument, which is the function. In this case, a lambda function defined as taking in one argument, tx. We call it tx. We can call it whatever we want, but in this case, it makes sense to call it tx. And that function will then go on to find the origin account of that tx. Now, the result of find transaction T, as we know, is a maybe transaction. The binding function, the second argument, is a lambda function that accepts one argument tx. We know that this tx is not going to be a maybe transaction because the function for the bind operator does not work. The type signature is not maybe A to maybe B, it's A to maybe B, right? So our bind operator it has a maybe transaction here, and it has a function here that works from transaction to maybe some type B. So the bind operator does the unpacking of the value to give it to this binding function. Tx, we call the argument Tx, and now we have basically what Tx represents is the result of this find transaction T, the value of the result, to be more specific. So not the maybe transaction, but just the transaction itself, unwrapped. And so we can use this Tx. We find the origin account of Tx. Then again, we bind to the next step. Find origin account Tx gives us back a maybe account. And we bind that to our next function, which accepts the origin, right? Because the find origin account will give us a maybe account. In our case, this is the origin account. So again, this lambda function that takes in this argument origin, again, origin here is not a maybe account, it's an account, right? Because the bind operator is taking care of the unpacking. That lambda function, what it does is finds destination account, but again calls the find destination account on tx. So tx, once we have it here, since this is all binded together, and basically the first lambda function encapsulates all the three lambda functions, tx is available for use not just in this step, but in any subsequent step. So even though we accept origin as the argument for this function, we don't actually use it directly here. We use the tx, and we will use origin in the next step, because the origin is, okay, we found it, so all we want to do is eventually return it. We don't need to do anything with it. In any case, once we find the destination account, the result of that we bind to the final function that then accepts the destination, the result of find destination account, the resulting value. And finally, we return origin and destination in a tuple, right? So this is the part where we use the origin from the previous step and the destination from the current step to return our final result. This sort of binding each step to the next is can remind us of the do notation that we already saw before with IO actions. And now it's time to reveal that the do notation is actually just alternative monad syntax, or syntax sugar if you like. So the do notation is not just for IO actions, it's available for any monad, and so the maybe monad as well. So we can write our find accounts function with the do notation instead of with the bind operator, and we can say the whole function is a do block where we first find transaction t, given t as the argument, we find transaction t in the first step, we get our transaction there. Okay, then next step, find origin account on that transaction that we got in the first step. The result of that is origin. Okay, so we have tx available now, we have origin available now. The last step is to find the destination account, again call it on tx, not on origin, and that will give us our destination. And finally we return the tuple origin and destination. Of course, we have to use return to wrap this tuple into the maybe type, and basically any do notation must return a monadic value. We'll go through one more example of a monadic type, which is the list monad. And we said before that the effect of lists are non-deterministic computations. Non-deterministic meaning there are multiple possibilities, multiple results possible. So the instance monad for lists is return x is simply the value x wrapped in a list. And the bind operator, if we have m, so basically a list of a's, right? Let's go through the type signature first. We have a list of a's, the monadic value here is the list. Then we have a function that operates on a and returns a list of b's, and finally the result is a list of b's. So we have m, which is our list of a's, bound to the function f. We can define this with list comprehension, because I think it is simple to see what's going on with list comprehension. So we have y, we build a new list with the elements y, and so let's see where this y is coming from. First, we have the list x, we have the list m, and we take elements from that list. We call those elements x. So for every x in m, we go get y, where y is the application of f to x. So the application of f to x is another list, right? Because f is a function that accepts one argument a, 1x, and returns a list of b's, right? So when we apply this f to x, we get another list. So we have to extract all the elements from that list, and we call those elements y, and those are all the possible results that we can get from binding M to F. So to summarize, chaining list operations will combine all the function application possibilities into one list. Here is an example of a simple code block to illustrate how binding on lists works. And here the example is modeling mitosis. Mitosis being a process where one cell splits into two exactly the same daughter cells. So we can model this process with the list monad, and in this case we'll represent cells with simple strings, and mitosis is then a string, a cell that gives back a list of strings, right? And it's simply a replicate 2. Whichever cell we got, once mitosis happens, we end up with 2 of those cells in a list. Okay, so we have a cell, right? A list of cells, so the monadic value, and then we bind it to mitosis, which operates on just the string, not the list of strings. And the result is cell, since the mitosis function is applied to all the arguments in this list, but that is only one cell here. On the other hand, if we chain multiple cell generations together, so we start with one cell, we bind it to mitosis, and then the result of that is again bound to another mitosis and another mitosis, then all of the cells in the lists are go through this process of mitosis, and we end up with more and more cells. So the first mitosis, the first generation, is going to create 2 cells. Then the next generation, each of those 2 cells is going to create 2 cells. So we end up with 4, and then the next generation is going to take 4 cells, and the final result is 8 cells, right? So that's how chaining or binding operations on lists works with the monad bind operator. Of course, as always, we can also use do notation. So here is another function, 3gens, which takes one cell and returns a list of cells, and the gen 0 is our first argument that we are given for the function, and then we say do mitosis on generation 1, that on generation 0, and that will generate generation 1. Then do mitosis on generation 1, that will generate generation 2, do the mitosis on generation 2, and finally we simply return generation 3, and that's the same as chaining 3 mitosis together with the bind operator here in the do notation. Like functors and applicatives, monads also need to satisfy certain laws to be valid. We have the left identity law first, which says that return x bound to f is the same as f of x. This makes sense, of course, because, okay, if we have some value x, some value of type A, we apply return to it, then return creates a monadic value of A, or the returns the x as a monadic value. That's our first argument for the bind operator, and the next one is f. So what is the bind operator going to do in this case anyway? It's just going to extract the monadic value f and apply fx to it, right? And it's going to give back the result. So really it's just going to do fx. The only thing it has to do is unwrap the monadic value x first. So basically we are wrapping the value for the bind operator, giving it to the function, and that's the same as simply not wrapping the value x and just applying the function to it. The right identity law says that m bound to return is equal to m. So some monadic value m bound to the return function is the same as m. This also makes sense because m is a monadic value, right? So if the function we are binding it to is just return, the bind operator is going to extract the value from m. So it's some value. The type is ma, right? Where a is the value wrapped, the monadic value ma, and the bind operator is going to unwrap it and apply it to the function return. And then, of course, the result of the return on the value is going to be just that same monadic value again. So, of course, this makes sense. M bound to return is equal to m. And the final law is associativity, which we, I think, say it's kind of associativity. It's not like 100% associative. Let's see why. So in general, we have a monadic value and two functions f and g, and we want to bind them together, right? So here the brackets are saying bind m to the function f and then bind that result to the function g. Okay, that's fine. And the law states that that is equal to m, the monadic value, bound to one function that is defined here as a lambda function that takes in the argument x, applies f to x, and then binds that to the function g. So we see that in the end, the result, the order of function application stays the same. So the results should, of course, be the same. We feed the monadic value to the function f first, which is the same in the right side. Again, m bound to the function x applies the f to x first and then binds it to g. So why did I say kind of associativity? Because we see in the right hand side we have this lambda function defined. If it was sort of real associativity, we have the brackets here, m bound to f. If we are really talking about associativity, then we would say m bound to f in brackets bound to g is the same as, I'll write it here so it doesn't, so m bound to f, oh, missing equal, oh, okay, this is terrible, but hopefully you can read it. So m bound to f bound to g. In the first case, we have the brackets here, m bound to f. With real associativity, what we would like to do is wrap the brackets around f bound to g, right? So we just move the brackets from m and f and apply it to f and g. But this is not type correct. That's why it doesn't work. Hopefully, I have explained enough about the bind operator that you can see why this wouldn't work. And if you don't see it already, I encourage you to try to write the expression that way, check the types on each of the bind arguments, and then hopefully you'll see why we cannot just write m bound to brackets f bound to g, but instead we have to write a lambda function that binds these functions together. So that's the end of this presentational part. We covered an introduction to monads. We saw the maybe monad and the list monad, and how we can use the bind operator to work with monads. And now let's go into the practical session where we'll explore this in more depth. Welcome to the last practical session of the course. Today we're going to be working on monads, and again we will be taking some exercises from the University of Pennsylvania Haskell course with the homework about monads. This session is going to get a bit complex, but we will take it step by step and no problems. Before we get into the actual exercises from the homework, let's do a quick recap of the maybe monad that we saw in the presentational part. So there we had an example of a transaction and a database and a function that, given a transaction, gives back the origin and destination account for that transaction. So let's do an actual implementation here. It's going to be like a simple implementation, more like a placeholder, but just to see that function in action. So we had our two types, one for transaction, which was just a string, and one for account, which was also represented by a string. Then we had our functions that in the presentational part were not defined, but just named. So find transaction. We're going to define them here with sort of placeholder implementations just to see this work. So find transaction is given a transaction will return maybe transaction, and we can say that for us this means if the transaction we are searching for is called testtx, then we will return just testtx. Right? So this is the only transaction we're going to find, and that will represent our case where we do find the transaction. Anything else is going to return nothing, since we assume that there is no other transaction in the database. Then we had find origin account that also takes a transaction and returns a maybe account. So find origin account, we can say it's the same thing, right? So if we have a test transaction, then we'll return just origin account, and find origin account for anything else is going to be nothing. And pretty much the same thing for the find destination account. If we are given a test transaction, then we'll return a destination account. Otherwise, we'll return nothing. Okay, so we can now write our function find accounts, which takes a transaction, and gives back a maybe tuple of two accounts. So find accounts written in the monadic way. Let's do it with a do block. I guess it's a very simple start. So we are given a transaction as the input to this function, and what we want to do in the do block is first find that transaction. So find transaction t, and then in the do notation we bind the result this way. So we say this is going to be our tx. Find accounts. This is going to be our tx, right? The result of this function, which is a maybe transaction, is going to be a transaction. Here the tx is actually unwrapped, so it's not a maybe transaction, it's a transaction. And then we have our second step is to find the origin account on that unwrapped transaction. That's going to be our origin. And the destination is going to be find the destination account, again called on the same transaction. Once we are done, we want to return the origin and the destination. Okay, so that's our find accounts function. And now we can load it to GHCI to see how it's used. So we load session 12. Okay, we have an import here for control monad random. This is a package we're going to use for the rest of the exercises, but we don't have it installed yet now. So I'm just going to comment it out that I can load this module. And okay, now we have our find accounts function and we need to give it a transaction. So if we give it some transaction, I don't know, tx, we get back nothing, okay? Because our test tx is the only one that exists and tx is not it. So all these things, basically when this ends up being nothing, all of the result is nothing. And we don't really need to specify it ourselves, right? Our function just binds the result one to another. And so the monad bind operator takes care of the nothing case for us. And if we have find accounts test tx, which is a tx that actually exists, then we get back a successful search for origin account and destination account. Okay, so that's the quick recap of what we saw in the presentation and how we can make some simple function with the maybe monad. And now it's time to get into the actual exercises for this session. First, a quick introduction to the topic of the exercises. It's the game of Risk. I don't know if you played this game before. It's a bit of an old game, a board game, where it involves 2 or more players and they are trying to conquer the world, and they battle over territories with armies and roll dice to determine the outcome of the battles. So what we are going to do is write a simulator which could be used by Risk players to estimate the probabilities of different outcomes before deciding on a course of action. Okay, so since rolling dice is involved, we are introduced to this rand std gen monad. So let's take a look at what this means. Since the battles are determined by rolling dice, we need some way of producing randomness. And here is an example of how randomness is produced in the language of Java with a pseudo random number generator. So you have this random class random, and then random gen is a new random, and a die roll is an integer that generates a value between 1 and 6 from this pseudo random number generator. It seems like we can't do this in Haskell because the output of randgen next int 6 may be different each time it's called, and Haskell function must always yield the same outputs for the same inputs. So this is where things get a bit complicated. We see that in Java code we can create a random object, and that represents a pseudo random number generator, and this generator has a bit of state. So it remembers a bit of state, a few numbers, and every time something like next int is called, it uses the state to actually deterministically generate an int and then updates the state according to some deterministic algorithm. So it's not really random, it's all deterministic, but the output is seemingly random. Right, it's seemingly random, and but okay, that's fine for us. It's a way of generating random numbers. So how to do it in Haskell? This is where we have the rand std gen example for how to generate 3 random integers in Haskell. So the rand std gen is a monad and the values that it wraps around are 3 ints, a tuple of 3 ints in this case. So here's something how this could work. It says get random, which will get us our random number, and then bind it to a function that accepts I1, then bind that to another get random that will get us I2, another get random will get us I3, and then finally we'll return I1, 2, and 3 in a tuple. And that's so it's again when it's returned, it's wrapped into the monad of rand stdgen. So what this says is basically that 3 ints is a computation inside of this rand stdgen monad, and this stdgen monad actually implicitly passes along a pseudo-random generator of type stdgen. So stdgen is our pseudo-number generator in Haskell, and rand is the monad that we're going to use. So the stdgen is actually defined in the standard Haskell library in the system.random. And okay, that's a quick introduction to how we are going to approach randomness, and we are getting more instructions here about the random stuff that we're going to explore now. So the exercise 1 is actually just about Cabal install monad random. So this is like a piece of code at the command prompt to download and install the monad random package from Hackage. So this is usually the case when we are writing Haskell code. We use packages and libraries from other people, so we will have to explore what this package does. So the instructions here are: take a look at the control monad random module, which defines various ways to run a rand computation. In particular, you will eventually, at the very end of the assignment, need to use the eval rand IO function. Okay, take a look at also at the control monad random.class module, which defines a monad random class containing methods you can use to access the random generator in a rand computation. So this is where the get random function, which is going to be probably the most important for us, comes from. However, you probably won't need to use these methods directly. Okay, so let's exit GHCI and let's install this package, Cabal install monad random. And now I'm gonna use --lib because that means install it globally pretty much. This is not usually a good thing to do, but since this is just an introductory course and we don't really deal with managing environments of our Haskell projects and stuff, and this is basically the only package we're gonna install, I'm just gonna do it this way because it's a bit simpler, and later on in the Plutus course we'll get more into project management and package management and so on. So it seems like the installation is successful, and we can go ahead and check this monad random package. So this is the front page, and here we have the control monad random class that the assignment talked about. So monad random is a class of a monad where, so this is the description, with a source of random number supply in hand, the monad random class allows the programmer to extract random values of a variety of types. So it does need a source of random number supply, which will be our stdgen, standard pseudo random number generator. And the two main methods here are get random r, which I think stands for get random range, because it takes a range from low to high, right? So it takes a range from low to high as a tuple, low and high, and a random number generator G returns a computation that returns a random value uniformly distributed in the closed interval together with a new generator, right? So the generator gets always passed on with an updated state to continue producing seemingly random output. And the other function is get random, where it's the same as get random r, but using a default range determined by the type. So it depends on which type we use, an integer, a char type, or our own type, and so on. Okay, so that's that one here. There are some other things that we don't really care about right now. There is also the control monad random, which has this module with the lazy. Okay, here we find the actual rand monad that we saw in the code. So we had rand and then stdgen, and then so rand stdgen is together a monad. And this is a random monad parameterized by the type G of the generator to carry. Okay, and these are the ways of running the monad. So such as run rand, unwrap a random monad computation as a function. So we have rand G as the generator and A as our type, the initial generator, and the return value is something like the type A, the random generated value of type A, and the new generator. Eval rand. So these are just different ways. So for example, eval rand discards the final generator, it just returns the value, and so on. For us, we will, as was mentioned at the end, use eval rand IO. So this evaluates a random computation in the IO monad and gives us back a type of IOA, right? So it wraps the A value into the IO monad once it's done. Another thing is on the monad random, the get random r and get random functions have this c random r for details, c random for details. So let's see random. This is actually from system.random. So that's this standard Haskell library. And this module provides type classes and instances for the following concepts: pure pseudo-random number generators. Random gen is an interface, so the type for a generator, and stdgen is the standard pseudo-random number generator in this library, which is an instance of the random gen. So programmers can supply their own instances of random gen if necessary, but we will be just using the stdgen as it's fine for us. So in general, random gen, so a pseudo random generator in Haskell has some methods, but we are interested in this class random A. And this class is the class of types for which random values can be generated. Okay, most instances of random will produce values that are uniformly distributed on the full range, but those types with a well-defined, without a well-defined full range, some sensible defaults will be selected. Okay. Basically, this is the class that has the methods random r and random that we saw in the monad random class. So the monad random has a type constraint of random A. So to use the monad random type class on type A, this type A must first be an instance of the random type class here, right? So if we define a new type, we have to define what random R and what random mean for that type, and then the monad random simply uses those methods with get random and get random R. Okay, so you see that this random A class constraint does lead to okay, it's in the control monad random dot lazy, but it is the same as from the system dot random. if we look at the source, oh, we can't see the source. We can't see the source, but we can see it here. So class monad m, we have get random r, which is random.random is the class constraint. And if we look at the imports in this module, we see that system.random is imported as random. So the random class referred to here is the system.random class. So let's get back to the code. We have explored this package a bit. We saw that it needs an instance of the random class from the system.random module. So we are ready to move on. And here it says in RISC-HS, we have provided a type, RISC-HS being the starter file for this homework. We have provided a type, new type, die value is type with a type data constructor dv, and it has one field undv, which is of type integer. So undv, I think this is pretty common in Haskell to prefix this un. I guess it stands for unwrap. So because if we use this field notation, then the name of this field is also the getter function for getting the actual integer behind it. So it's sort of like undv, unwrap dv to get the int. And this type is used for representing the result of rolling a six-sided die. We have also provided an instance of random for die value, so allowing it to be used with monad random, as we just saw. And the definition, a die, which is of type rand stdgen die value. So the monad random for the die value type, and die is simply the application of the get random function of the monad random package for our die value type. And it represents the random outcome of rolling a fair six-sided die. Okay, so basically here is the part that we have defined for us. New type die value is, as we saw, dv, undv is int, and here it derives some classes, eq, ord, and show, and it derives num as well. And usually it's not possible to simply derive num, but this file uses the language extension generalized new type deriving, which allows to derive the num type class. I'm not going to get into how exactly it does it, but you can find out more by looking up this generalized new type deriving extension. Also, now that we have our control monad installed, we can remove this comment, so we actually import it without errors. I think we just need a refresh here, because now with the module imported, everything should be fine, but we'll see. Anyway, we stopped at new type die value. Okay, derives the num type class. We have the first function defined as from the previous video, which is simply function that operates on a tuple and applies the function to the first argument of the tuple. Let's try to reload. See if we can get rid of the type errors. Okay, so now this works. We have imported our newly installed package. The IDE knows about it, so it can give us the types as it should. Okay, so we stopped here. The instance, here we are given the predefined instance for the random. This is the random that we said comes from system random for our type die value. So this is going to maybe get a bit tricky. to understand. Of course, we can just skip it over and basically it's given for us, and you know, it's an instance for the random. We can take it as it is and just use it because we know it probably works. But it's good to try to understand every line of code. So we saw that the random type class has these methods, random and random r. And random is sort of the default method for just getting a value from the default range, and random r is get a value from a given range. So random covers the entire range, and random r can be from a specified range. So what happens here? We have a function composition, and okay, my IDE is already given us the type signatures that we can insert here. It does help if we have the type signatures. So I'm just gonna click them. Basically, we know that the random function needs a random gen g, and the random gen, as we saw, is the interface for a pseudo random number generator. In our case, we will be using stdgen as our random number generator. But this is a very generic type signature, so it's using a random gen as the type class. And so we have the generator, and it creates a die value for us that is a random roll of a dice and gives us back the new generator with the updated state. So how does this work? We have function composition. So the function on the right will be applied first, which is random r for the values 1 and 6. So 1 and 6 here are integers. So this basically means, since integers, we don't see the definition here, but for integers there is already a random instance defined. So random r for two integers 1 and 6 will give us an integer that is inside this range of 1 and 6. So it will either give us 1, 2, 3, 5, 4, or 6. And then once we have that integer, we will, since this is function composition, we will apply dv to the first argument of the tuple we get back, because we know that we get back a tuple of not die value here, but we get a tuple of int g. So we apply the dv data constructor for our die value type to the first argument of the tuple. So basically this expression is the same as writing this thing. This is now a redundant bracket, but so we apply first dv to this result. And then of course from int, from a tuple of int g, we go to a tuple of die value g. Okay, what about the random r for our die value type? So random r also needs a random gen g, but before we give it the generator, we give it a range, right? Die value and a die value, the first one representing the low and the second one representing the high of the range. And we get back the same thing, value of die value and the updated generator. So random r for this tuple of die value is, again, at the end we're going to apply first dv, but first we compose random r again. And so note that here we have random r we are defining the method random r, and we're using random r in the definition. So this may seem like recursion, but it's not, because this random r operates on our type of die value, while this random r, as we see, just like this one, operates on integer values. So the arguments that we give to random r in this case are max 1 and undv low. So we have our low, which is die value type. So to get the integer behind it that's wrapped, we use the undv getter function. So this is going to be the integer of the die roll for our low range. And we say max 1 and undv low. So if we get, if our undv low is, for example, the number 2, we're going to use 2 as the lower limit for our range. But imagine that we put in a 0 or a negative number, -1. Then we use this max function to make sure that our low range must be at least 1. It cannot be less than 1, right? Because it doesn't make any sense for our die roll. And the same on the high, the high value for the int range. We have a min 6 and undv high, which is our second element of the tuple of the range. So that if our high range is above 6, we reduce it to 6 because we select the minimum value, because again, it doesn't make sense to go above 6 if we are trying to model a 6-sided die. Okay, so those are the two functions, random and random R, for our die value. And finally, we have the die function, which is of type rand std gen die value. So this means die is a function that is a computation in the rand std gen monad that produces a die value type. And die is simply a call to the get random function for our die value type. So it's basically just a helper function for us to generate one roll of a dice. So we have sort of the introduction done. We understand the initial definitions that we are given, and now we can move on to the actual rules of the Risk game. So the rules of attacking and Risk are as follows. There is an attacking army containing some number of units and a defending army containing some number of units. The attacking player may attack with up to 3 units at a time. However, they must always leave at least 1 unit of their army behind. So if they have 3 total units, they may only attack with 2 units. The defending player may defend with up to 2 units, or 1 if they only have 1. So defend is maximum 2, and attacking is maximum 3. To determine the outcome of a single battle, the attacking and defending players each roll 1 6-sided die for every unit they are using. And so the attacking player rolls 1, 2, or 3, depends on how many units are attacking, and the defending player rolls 1 or 2, depending on how many units are defending. The attacking player sorts their dice in descending order, so the highest first, and the defending player does the same. The rolls are then matched up in pairs, so starting with the highest roll of each player, then the second highest. For each pair, if the attacking player's roll is higher, then the defending player suffers a casualty. And if there is a tie, the defending player wins, so the attacking unit suffers a casualty. So here is an example of a battle in the game of Risk. Suppose player A has 3 units and player B has 5. A can attack with only 2 units and B can defend with 2 units. So A rolls 2 dice and B does the same. Suppose A rolls 3 and 5 and B rolls 4 and 3. After sorting and pairing up the rolls, we have, so A threw two dice and he got 5 and 3, and B got 4 and 3. So we order them in descending order and then we make pairs. So the pairs are 5 and 4, 3 and 3. A wins the first matchup, 5 is greater than 4, so B suffers 1 casualty. The second matchup, 3 and 3, they are the same, so it's won by the defending player B, so the attacking player suffers 1 casualty. If A wanted to attack again, they would only be able to attack with 1 unit because they lost 1. And B would still get to defend with 2, because I think he started with 5, so he has 4 left, so he can still defend with 2. Okay, those are the rules, and now it's time for exercise 2, which will actually get us writing some code. Given the definitions, type army int. So given these definitions, I can comment them out. So we have a type army, which is a type synonym for an integer, which represents the army, the number of units. And we have a type battlefield, which has the battlefield data constructor, and the battlefield is composed of attackers, which is a type of army, and defenders, which is a type of army. Here I put a deriving show, as we might need to show the battlefield later on. And so given these two definitions, write a function with the type battle that is of type signature, takes in a battlefield and returns a rand state gen battlefield. So basically it returns a new battlefield that is computed in the random stdgen monad, because it includes rolling dice, so it includes random events, so it's computed in this random monad, and it produces a new battlefield, which is the result of that computation. It should simulate randomly rolling the appropriate number of dice, interpreting the results, and updating the two armies to reflect casualties. So this battlefield is the one that's that calculated the results and updated the state of the armies after the battle. You may assume that each player will attack or defend with the maximum number of units they are allowed. So this makes things easier. So we always attack and defend with the maximum amount of units we can. Okay, exercise 3 is for later. So let's get started with this exercise 2. So to start off, we can start just thinking about how we want to do this. So like what are the steps we need to take in order to get to the final result. So you say the first step is we are given a battlefield with some attackers and defenders, and we can calculate the number of attackers, defenders for a battle. Right, so we know that if there are 3 attackers in the battlefield, only 2 can actually attack, because one has to be left behind. So that's the first step. We can calculate basically how many times we need to roll the dice, and then once we have the numbers, we can roll the dice how many times, right? The attacker plus defender number of times. So if there are 3 attackers and 2 defenders, we need to roll the dice 5 times. We also need to separate the roles for attacker and defender, and we need to sort the results in descending order. Okay, so then we have the roles. We have 3 roles, for example, 3 roles for the attacker, 2 roles for the defender. They are sorted in descending order. So now we need to create the pairs that we're going to compare to interpret the results. So create pairs of attack, defend. I guess this will be like a tuple attack, defend. Attack, defend roles. I guess that can be just one step. Then we need to interpret results, or in other words, calculate casualties on both sides. And finally, we need to update the battlefield with casualties from the last step. Okay, I think that's pretty much what we need to do. So we'll write the battle function at the end, and we'll start with these simpler helper functions that are going to eventually get us there. So the first thing is calculate the number of attackers and defenders for a battle. So we can call this function get armies, that given a battlefield gives us a tuple of army. So a tuple of attackers and defenders. And so get armies accepts a battlefield as its argument, and we can use pattern matching here actually to say battlefield, and it has some attackers and defenders, because that's how our type constructor works, right? It takes two arguments, attackers and defenders. Okay, and we know that this function needs to return a tuple. The first one is the number of attackers in this battle, and the other one is the number of defenders. So the number of attackers is going to be 3. If there are 4 or more attackers, it's always going to be 3, right? Because the assumption is the player will always attack with the maximum number of attackers possible. So if attack is greater than 3, then it's going to be 3. Else, else, so it means it's either 3 or less than 3. So if it's 3, we can only attack with 2. If it's 2, we can only attack with 1. So also if it's 1, it's we can only attack with 0. So it's always going to be attack minus 1, because that one needs to stay back. So that's our number of attackers, and the number of defenders is going to be 2. It's going to be always 2, except if there's only one defender. So we can use the min function, where we say it's going to be either 2, or if defender is less than 2, then it's going to be def, right? So if def is 1, then the number of defenders is 1. If it's 5, the number of defenders is 2. Okay, that's our get armies function that completes the first step to calculate the number of attackers and defenders for a battle. We can even test it out. So load session 12, and then we need to define some battlefield. So battlefield I guess I can just do like 10 and 10. Yeah. And now if we say get armies from our battlefield BF, we get 3 and 2, right? Because the attackers are going to attack with the maximum number, which is 3, and defenders are going to attack with the maximum number, which is 2. Okay. We can also test a case where there's only 3 attackers and 1 defender, and in this case we get 2 and 1. Because 1 attacker needs to stay back, it can only attack with 2, and defender is going to attack with everything, defend with the 1 it has. Okay, so that's the get armies function. Now let's go into the rolling the dice. We can call this next function get rolls, and the type signature, so we can take what we got from our get armies function, so army. So we get a number of attackers and defenders, and we return. So now we are going to roll, and we're going to get some random numbers, and we're going to get them for the attacker and for the defender. So we can return a tuple of the rand std gen monad for, now it's going to be a list of die value, right? Because imagine we have three roles, then we want to create a list where the list contains the results of the 3 roles rather than just one. And so the first element is going to be the attacker roles, and the second element is going to be the same type, but it's going to represent the defender roles. So get roles of a tuple. So we accept a tuple, we have attack, we have a defense, and now we want to actually roll the dice. So to roll the dice, we say die, right? Because we have our function die that gets us one die roll for our die value type. But in this case, we don't want to do it just once, we want to do it many times. And so we can use this function called replicate m, which is a very useful function that takes in an integer and a monadic value and returns a monadic value of a list of a's, right? So the monadic value here was a and returns a list of a's. So it basically repeats the same action the int number of times and stores all of its results in a list. So this is exactly what we want. We basically want to replicate m how many number of times. So for attackers, we want the attacker number of times, and what we want to do is what the action we want to replicate is die. And same for the defenders, except here we want to roll the defender number of times, and we also roll with the die. So this is okay. Now we get the roles, but we rolled the dice attacker plus defender number of times. We separated it for attacker and defender. We can also sort the results in descending order here. Okay, so how do we sort the results here? In general, we already saw that we can use sort. We can sort a list. By default, that's going to be ascending order, and then we can compose a reverse function to it to sort it in descending order. Now, sort is not in scope because we have to import it. Okay, we have a lot of code. So import data.list sort. Okay, now the types don't work anymore. So this is basically our function that we want to use. But of course, this function operates on lists, and we don't have a list. First of all, we have a tuple here. So if we want to apply a function that works on the underlying type, we have to map it over a tuple. So for every list in the tuple, we will fmap this function. That's almost fine, but we still have a problem with the types, because this would work for a list of a tuple of lists, but we don't have a tuple of lists. We have a tuple of monadic value of lists. So basically, to apply this fmap reverse sort to replicate m attacker die, which is of type rand std gen die value, we want to apply it to this list of die value. So then we have to fmap it again, one time for the tuple type and another time for the monadic type of rand std gen. So for the second one, we can use the infix fmap operator, and now the types are fine. So let's try to go through this one more time. Here we have a tuple of random std gen a list of die values. We want to operate on this list of die values to sort it in descending order. To do that, we map the reverse.sort function, which will work on this list. But since we are not operating on a list, but a monadic value, we have to map it over the monadic value, fmap it over the monadic value, because we know that every monad is also a functor. So that would work, except that for another little thing, that we don't have just one random std gen die value, but we have a tuple of two of them. So we have to fmap this function over the tuple as well. So we have to use two fmaps. And now this completes our sorter results in descending order as well. And we can move on to creating the other helper functions. Our next step is to create a function that will create pairs of attacker and defender roles that we can compare. So basically, this will be a list of pairs. For this function, okay, we can call it create pairs. And I'm going to again take what our getRoles function gives us. The tuples for the attacker roles and the defender roles as monadic values. And I want to return just one monadic value, rand std gen, of the type of a list of pairs of die value and die value, right? So this will be our pairs, die value, that we combine from the given roles. So create pairs is going to take a tuple of attacker and defender again, and in this case we know that attacker and defender are monadic values. So we can bind them to a function that operates on monadic values. So we can say, okay, we have this die value, we want to access it some way, but we can only access it in the monad. So we bind this attacker monadic value to a lambda function, and the argument that this lambda function is going to get is this die value unwrapped, right, from the attacker. So we can say this, we call this attack roles. And what this function is going to do. Right now, we don't need it to do anything with attack roles, actually. What we want to do actually is just get the defender roles first. So this function is just going to take def and bind that to another function, and we know that this function is then going to be def roles. It's going to operate on, again, a list of die values, which we call def roles. And now this function can finally return something. And what do we want to return? This list of pairs of die values. So we somehow have to join this list together. And there is a function called zip, type of zip, which takes in two lists and creates exactly what we want. So if we say a list of 1, 2, 3, zip it with a list of 1, 2, we get back pairs 1, 1 and 2, 2. And okay, actually, like, we are working with descending order lists, right? So 2, 1. So the first element from the first list is matched with the second element from the second list, and the second element from the first list is matched with the second element from the second list. So the pairs are only created for the length of the shorter list, right? So here the one from the attacker roles is excluded, as it should be, right? We create only the first possible pairs, and that's exactly what we want. So what we want to return is simply zip applied to attacker roles and defender roles, right? So attacker roles and defender roles, we know that zip operates on lists. So if this is not complaining, then of course we know that attack roles and defend roles are definitely lists, because the bind operator unwraps this ATT value, which is a monadic value, rand stdgen, but the underlying value is a list of die values. So attack roles here is a list of die values. Same goes for the def roles. So now we have our pairs, and we need to somehow interpret results and calculate the casualties that each side suffered as a result of the battle. To calculate the casualties, we can create a function, calculate casualties, and we can have the type. So this is pretty much an exact computation. We don't need the monadic values here. We can just take the list of pairs that we're going to get here, although here it's in the monadic value. We can have this function just accept a list of die value pairs, and it's going to return an army, signifying the casualties on the attacker side, the number of casualties on the attacker side, and the number of casualties on the defender side. So calculate casualties is therefore, we have a list of tuples, and as a result, we produce just one tuple. So this should remind you of something like folding, right? We have a list, we go through it, and we calculate just one tuple from all the elements. So I'm gonna use fold r here, and fold r accepts some function f and some starting value. So for us, the starting value is obviously going to be 0 and 0, and then we are going to calculate the casualties. So fold r, function a to b to b, and the starting value b, and then the type of a. So we can leave the type out, with that last argument out, because we can use ETA reduction. And we just need to define f. So what is f going to be? We know that f is a function that accepts die value tuple, and an army, and returns an army, right? So the second argument, army, is our accumulator value that is being returned, and die value is the next element from the list, so a pair of two die values. So the die values will be a tuple. We can say, let's just call it A and D. So this is the role. Let's just say role A, role D, role attacker, role defender. And the other tuple is our current casualty count, right? So we can say casualties A and casualties B. Basically, our second argument is this, which starts at 0, 0 and gets updated on every run. So here we can use guarded equation, for example, and we can say that we are basically comparing roles, right? So if role A is greater than role D, then that's our case where the attacker wins, and so casualties A stays the same. The attacker does not suffer a casualty, but casualties, oh, sorry, not B, but D, casualties D is +1 because defender lost, so he suffers a casualty. And in any other case, otherwise, in any other case, the defender wins, right? So the casualties A gets a +1, and the casualties D stays the same. So this looks right, and here we can say, okay, we got a list xs, and we can, apply it to the list now. But like I said, we can just leave this out, and because it gets implicitly applied. Okay, so that's our calculate casualties function. We can even test it out. If we have a pair, we have some pairs of die values. So a list, let's say attacker roles is a list of dv5, dv4, dv4, dv3, and defender roles is die value, let's say 5 as well, dv3, dv2. Then the attacker should lose this first pair, 5 and 5, right? And the okay, yeah, we need to zip them together, I guess. Zip attack rolls and defend rolls together, and now zipped is dv5 4 3. Okay, so now we can use the zipped to actually supply it to this calculate casualties. We apply it to zipped, and we get one casualty for the attacker and 2 casualties for the defender. Well, that doesn't sound right. Oh, right, because we have, it doesn't sound right to our rules, but the way we applied it, it does sound right, because we zipped 3 rolls, but the defender can have a maximum of 2 rolls. So now it's correct. The calculate casualty zip now calculates 1 casualty for the attacker and 1 casualty for the defender, right? So the attacker loses the 5 equals 5, but wins the 4 is greater than 3 roll, and that's fine. So that's our calculate casualties function now, and all that's left is to update the battlefield with this casualties count. So this should be a quite simple function. We can call it update battlefield. And so we take in a battlefield, the starting one. We take in the casualties, which are represented as a tuple of army, and we give back a new battlefield with the updated counts. So update battlefield takes in as arguments the battlefield and the casualties A, casualties D, and we know that it will return a new battlefield, so we can use this new battlefield where attackers and defender numbers just need to get updated, right? So we have battlefields. What's going to be the new number of attackers? Where it's going to be attackers from the first battlefield, attackers BF, minus, so from this tuple, the first element represents the casualties for the attacker, right? So we can use the function first, which accesses the first element of the tuple, and our tuple, sorry, we don't need to do it because we already used pattern matching here, so we can just say casualties A, and our defenders are going to be defenders from BF minus casualties D, which is the second element from the tuple. And that's our updated battlefield. We can test it out just to make sure it works. BF, we had a BF defined. Battlefield 3 1, and then let's say casualties are 1 1, and then we say update battlefield BF with casualties CAS, and then the new battlefield has 2 attackers and 0 defenders, which for this case is the correct update. Now all that's left to do is actually write the function that we are supposed to write, battle, which takes in a battlefield and produces this random dice roll computation to produce a new battlefield in this monad random. So for this battle function, battle takes a battlefield and produces a rand stdgen battlefield. And so battlefield accepts battle accepts battlefield as an argument and returns monad. Okay, so what do we want to do here? Let's take a look at our helper functions, right? One of the first things we want to do is actually figure out how many times we are going to roll. So we need to get armies. So I'm just going to put this in the where clause right away. We're going to have armies are equal to get armies from our battlefield. So the result of this is a tuple of army, which is exactly what get rolls takes to produce some first monadic values. The create pairs then operates on those monadic values to produce another monadic value, which is the list of pairs. Okay, then we have to somehow unwrap this list of pairs to use it with calculate casualties and finally update the battlefield and return. Okay, so let's apply get rolls. We applied to armies, right? So get rolls gets applied to the armies, which is the result of get armies function application. We get some monadic values, and then the result of this is feed for the next function that creates the pairs. So we can just use function composition here that says create pairs once you got the rolls, right? You can even put it in brackets to make it clear. We're going to combine these two functions and apply it to armies, which means get rolls for the armies, and then get rolls is going to sort them and everything, and then create the pairs from that result. Okay, so our result is finally going to be the result of create pairs, which is a monadic value. So now we want to use the value of a list of die value pairs in the calculate casualties function. So we have to somehow unwrap. We know that we can use the bind operator for that. So whatever the result of this function application is, it's a monadic value, so we bind it to our function here. We're going to define as a lambda function, and we know that the underlying monadic value we are working with is a list, so we'll just call this xs, or we can even call it pairs. And so the question is what we want to do with those pairs. Well, we want to calculate casualties and we want to update the battlefield. So we calculate casualties based on the pairs. Okay, that's one thing. That gives us an army, which we need to supply to update battlefield to then produce a new battlefield, right? So at the end of the day, what we want to do is update battlefield, then the first battlefield, the initial one, the BF, and we want to update it with the casualties that we get from the function application calculate casualties to pairs. So we want to update it with this value. And that seems okay, right? Except we are just missing our return statement, right? We need to, since we are dealing with a monad, we need to, because update battlefield is going to return a battlefield, but we need to return a monadic value of battlefield. So we're going to return all of this together, and the types are now fine, and this is our battle function. I guess we can go through it one more time, just try to make it more clear. So first we get the armies. The first step is just calculate how many defenders and attackers are involved in this battle. Okay, then once we know that, apply get roles to the armies, which will give us a monadic value, a tuple of monadic values, the list of die values for the attacker and the defender. From there on, we compose the result of that with the create pairs function, which takes exactly the result of the get roles function application, and produces another monadic value, which is simply a helper function that joins these two roles together into pairs. Then we know that this is a monadic value. We bind it to our function. So the binding unwraps the pairs. We get pairs as a actual list of die value pairs. And because of that, we can use the calculate casualties function, which takes in not a monadic value, but just the list of die value pairs. Once we apply that, we know we get the tuple with casualties from each of the armies, and we update the initial battlefield BF with those casualties, and we return the result to get back to remain in the monadic value, right? So everything is encapsulated in the rand std gen monad. Okay, that's the battle function. So let's test it out. To test it out, we will write a main function that is going to have an IO battlefield type. So this is where we'll use the eval rand IO that was mentioned at the start, and we saw that it runs the rand computation and finally returns an IO in a type of IO. So main, we can write it as a do block. We want to first create some kind of a battlefield. So we say let bf is equal, and here I use let in the do notation. So this is different from let in expressions. This is a let statement. So let used in do notations is used when you want to assign something that is outside of the monad you're working with. So now, right, for BF, I just want to create a battlefield, right? Just a battlefield type. It doesn't have anything to do with the random monad or the IO monad. So I can do this with the let statement. So that's the difference between the bind from some statement that generates some value x, because x is always going to be a monadic value in this case from bind, but let bf is not a monadic value, it's just a battlefield here. So that's how you use let in do blocks. And I'm going to say battlefield with 50 attackers and 30 defenders. Okay, so what I want to do is run eval IO on this battlefield. Variable not in scope. Sorry, it's eval rand IO. Eval rand IO. Battlefield could not match the Battlefield, right, of course. We don't want to evaluate the battlefield. We want to evaluate the battle on the battlefield. So battlefield will actually give us, actually does the computation in the rand stdg monad. And eval rand IO will convert it into the IO battlefield monad. Okay, so hopefully this prints something out when we run main. Yes. So here is a simulation of one battle, right, where the attacker lost 1 and defender lost 1. Here is another simulation. This time attacker lost 2, again 1 and 1, again attacker lost 2. Are we going to see defender losing 2? Not really. There we go. So in this finally run, the defender lost 2. So you can see that the results are random, and even though the input is seemingly the same, we are producing different results. So this is the randomness coming in, but it's all encapsulated inside the random monad. Okay, so our battle function works, right? We have a battlefield, we simulate a battle, and we get back some results. So now we can go to the exercise 3, which is a continuation on this, and it says that usually an attacker does not stop after just one single battle, but attacks repeatedly in an attempt to destroy the entire defending army and thus take over its territory. So now we need to implement a function invade, which again takes a battlefield, and the result is again the same, the rand stdgen battlefield, but this time it simulates an entire invasion attempt, that is repeated calls to battle until there are no defenders remaining or fewer than 2 attackers. So until either one of the sides wins. Invade is basically going to be just recursive calls to the battle. And you can start, so we know type signature takes a battlefield, creates a sort of a final battlefield that cannot progress anymore. Okay, so we take a battlefield. Okay, so what is this function going to do? We can use guarded equations, because we basically have our base case where the battlefield does not have enough attackers, or there are no defenders left. So we can say attackers from BF if this is less than 2, right? If it's only 1 or less, then you cannot attack anymore. Or if defenders BF is less than 1. So if this expression is true, then we are simply going to return battlefield, right? Because there's nothing to be done. That's the end state of the battlefield. Otherwise, we will do a battle, and we'll do a battle on the battlefield. That will give us the monadic value rand stdgen battlefield, which then we can bind to the next invade call, right? So we do one battle on the battlefield, we bind that result to invade, and then invade is going to get the battlefield, which is the unwrapped value from this monadic type of the result of battle BF, and it's going to keep going until it reaches this case where either there are no attackers or defenders, no available attackers or no defenders. So we can again test this. I'll put the main function here now. We again get the battlefield, but we don't evaluate the battle, we evaluate invade. Let's this. I'm just gonna comment it out instead of removing it. Okay, we reload and we say main. Sorry, I didn't put invade. Invade. Okay, reload main. Okay, so now the invasion is fully simulated. So this time there are 10 attackers left once all the defenders are gone. In another one, there are 4 defenders left and there are no more attackers. So attackers is 1 and so on. We can get random simulations of the invasion attempt. Okay, that's exercise 3 done. The last exercise for the session is exercise 4, which says finally implement a function success probability, which takes a battlefield and generates a rand stdgen double instead of battlefield, which runs invade 1000 times and uses the results to compute a double between 0 and 1, representing the estimated probability that the attacking army will completely destroy the defending army. For example, if the defending army is destroyed 300 out of the 1000 simulation, then success probability should return 0.3. Okay, so let's do this one. Basically, we want to replicate the invasion 1000 times. And then do something with the results, analyze the results basically. So success probability, we can write a do block, since we know that the first thing we want to do is run invade 1000 times and save the results of those 1000 simulations. So we already used the replicate m functions when we had to perform an action multiple times. So we wanted to roll a die multiple times and get the results of all the rolls in a list. So now we want the exact same thing, except we're not rolling a die, we're simulating the invasion. So we can, the result is going to be a list. Let's just call it XS. And we are going to replicate M 1000 times the invade battlefield. So battlefield is a type here, right? So invade battlefield gives us a monadic value. We replicate that 1000 times, and the results are all in this list. So there are 1000 elements in this list. Each of them is a battlefield. So each of them is something like this: battlefield where either there are some attackers and no defenders, or there are defenders but there are no more attackers. So we have to, now that we have the results, we have to analyze them. In other words, we have to see in which case did the attacker win, how many times, and calculate some probability from that. So we can have a helper function. We can call a helper function f that operates on the on a battlefield, right? It analyzes one battlefield, and for this battlefield we can use guarded equations. So if we can say if defenders of the battlefield are 0, that means the attacker won. So since this probability says estimated probability that the attacking army will win, so we can say this is sort of a win, and we can replace the battlefield with just the number 1, 1 representing a win, right? And otherwise we can just say 0, okay, because that's the case where the attacker loses. So now we have this function, and we can map it over XS. Now I'm not sure, can we maybe use let here? So let probabilities or results, let result equal to, so f map this function f over XS, right? Then we have the result, and now we have to return something. What we have to return is a double, right? So we have our results here in the res as a list of 1 or 0. And basically what we can do then is sum this list up and divide it by 1000, and that will give us the probability, right? The types seem okay. So let's go through it one more time. We first replicate 1000 times the invasion. We get the result of 1000 simulations in XS, which is a list of battlefields. We then fmap this helper function f that processes each battlefield to say, did the attacker win or did the attacker lose? So this is represented by integers 1 and 0. And then we simply return the sum. So all the ones are going to be summed up. So if there's 300 wins in there, the sum is going to be 300, and divided by the 1000, which is the number of simulations that we did. This should give us the probability. Okay, we can again test it. We need to use the main function here. In this case, I need to comment this out because we will not be returning IO battlefield anymore. We will be returning IO double. IO double. So we have a battlefield. We comment this one out. And now what we want to do is evaluate the success prob on this battlefield. So let's reload this and we run main. It takes some time because it has to run 1000 simulations. And this time we got the 0.736 as the probability. Next time 76. So of course it's not always going to be the same because it's kind of random. So the probability is not exact. 77 and so on. Maybe we can increase the number of defenders. And let's see. Oh, now it's a very small number, it seems. Of course, the defenders have the advantage. Okay. So for this battlefield, it's 2.6. Anyway, that's the success probability function done. And that's this practical session completed as well. And it's the end of the Introduction to Haskell course. So today we probably had the most complex practical session of all, which makes sense because it deals with monads. Monads are quite difficult to grasp. Hopefully this was helpful. Anyway, thank you for watching and staying until the end. As I said, this completes the Introduction to Haskell video series. And the next one is going to be an Introduction to Plutus video series, a series about programming smart contracts on the Cardano network. So stay tuned for that, and I'll see you in the next video. Bye.